Hello everyone, welcome to NPTEL online certification course on fundamentals of food process engineering. So, our first lecture started with food rheology. Rheology is a very important parameter for to identify any material property. So, in today's class we will see that what are the various kind of relation we can observe in the food rheology. So, first let us see what is rheology actually. The definition is rheology is the branch of physics in which we study the way the materials deform or flow in response to the applied forces or stresses, right. So, whenever we do any food processing operation, that means the food which is either liquid, solid or semi solid, that is exposed to certain kind of forces. Okay. So, forces again may be of different types, and that force will cause certain stresses to it, and because of that stress the response of different food is in different way, right. So, that is the concern of our study. Now, in the context of physics, flow can be defined as the continuous deformation over time. Okay. So, flow is the continuous deformation over time, and it can be said that all materials can flow. All materials can flow, but the difference is that the degree of flow will differ in case of different material. Okay. So, the ability to flow is not only possessed by the gases and liquid, because we know obviously these materials flow, but also by the solids, okay, but not with the same degree as it happens in case of the liquid and the gases. Now, the main factors that influence the flow are temperature and time, okay, because temperature is when we increase the temperature, most of the cases in case of the liquid, the their flowability increases. That means, there is a property that is providing the resistance of the flow that is going to decrease if we increase the temperature. Similarly, if the same temperature increase can cause a reverse property change in case of the gases. Okay. And since the food is mostly mixture of different composition and different kind of material, not only pure liquid, there is suspended matter in it, okay, dissolved matter in it. So, generally the behavior of food in terms of rheology, if you want to assess, that is become a typically complex phenomena. Okay. So, first we will see the elastic property. So, elastic property which is basically seen by the solid material. Okay. So, what is that? This is a force and deformation behavior, and if we want to assess that what are the different kind of forces, the first thing is that the first kind of force that we can analyze is that when the food or any material is exposed to uniaxial loading. Okay. That means, in one direction, in axial direction, either we are pulling the body from both the side, or we are compressing it from axial direction. So, in that case what happened, that there is some elongation we can observe on the body in the axial direction or in the direction of the applied force. Okay. So, this kind of force causes, this is called the normal, the force is acting in the normal direction. So, the stress generated is called the normal stress, right. Then if we look into the second picture, where from all the side force is acting on a body, okay, from all the three direction, that is x, y and z, the force is acting on the body and therefore causing the decrease in the volume. Okay. So, this kind of phenomena, this is called the bulk compression loading, which results in volume change in the solid body. Okay. So, the first force, that is axial force or uniaxial loading, that can cause change in one dimension, one direction. However, the bulk compression changes the body from all three sides, okay, all three direction. Now, the next one kind of force may act on a body, that is called the shear force. Okay. So, what is that? Let us say first we can consider a block, okay, resting on a floor or on a ground, and if we apply a force F t parallelly on the top surface. Okay. So, top surface will try to pull it on the x direction because of this force F t, whereas the bottom surface, which is fixed on the ground, will have a reverse directional stress, because this will not try to flow with the upper layer. So, because of inertia, this kind of behavior we can observe. So, in this case what will happen, the body will deform, okay, body will deform, but not the similar way it has happened in case of axial loading or bulk compression, but it will some kind of bending or twisting will be observed, and the body will be deformed from its longitudinal position by an angle gamma, and that angle gamma will be the from using that gamma we can measure the deformation by the distance the layer has moved from its equilibrium position divided by the distance between these two layers. Okay. So, that is basically tan gamma, right. So, then these are the different kind of forces that can act on a body, and because of these three different kind of deformation we can see. Now, the thing is, as we have mentioned that when we apply the uniaxial loading, that time it may be when we are pulling the body apart, it is tensile force, and when we compress the body from both the side, it is compressive force, and we know that force divided by the area on which it is acting give us the concept of the stress. So, we can get the tensile stress or compressive stress. Okay. Now, why this concept of stress is more important than the force and deformation behavior? Because if we look into these two diagram, let us say that these are of the same material. Okay. So, this is also material A and this is also material A. Okay. However, their shape is different. Okay. So, in the first one we can observe that length is high compared to the width, height is more, you can consider in that way. Here the height is less and width is high. On both the material we are applying the same axial force F. Okay. So, since the area is different and the geometry of the figure are different, so both the cases the deformation we can observe in terms of delta L, okay, that may vary. I mean that will definitely vary because these two shapes are different. Okay. So, the delta L here is much higher compared to this delta L. That means, if you analyze the force and deformation, that cannot give you the property which is a material property, because this delta L will change from different shape of the material. So, we want something that will be of the material property, that does not change when the geometry changes, right. So, because of that, to understand the material rheological property, force and deformation will be changed to some other parameter, that is stress and strain. Okay. So, the elastic property of a material can be best understood by the relation between the stress and strain, and the quotient of the force over area is called the stress expressed in Newton per meter square. So, sigma that is equal to F by A, whereas the relative change in length is called the strain, which is the dimensionless parameter. So, epsilon that is equal to delta L by L. Okay. So, relative change of the length. So, when a material exhibit a linear relationship between increasing stress and strain, it is said to be a classic elastic material that follows Hooke's law. Okay. So, Hooke's law, if we can plot the stress strain diagram, that we will do now. So, that is expressed by the Hooke's law, that is stress is proportional to strain and the proportionality constant is E, which is modulus of elasticity. Now, this modulus of elasticity is the material parameter. Okay. So, whatever may be the shape and size of the same material, we can get the modulus of elasticity fixed. Okay. So, that is the advantage of using the stress strain analysis of any material, right. So, so the next is we will now look into the general stress strain diagram. Okay. So, let us see that here we have expressed the strain in percentage in the x direction and stress in Newton per meter square in the y direction, and we try to increase strain and we measure the record stress continuously. So, along the graph, if you can follow, initially we are getting a straight line portion. Okay. So, in this straight line zone, the stress is proportional to strain. Okay. So, the material obeys the Hooke's law. Okay. Material obeys Hooke's law here. Now, after this portion, there the curve starts deviating from linearity, right. And till this, again we can consider the proportional limit, because till then we can consider more or less straight line behavior. Beyond this point, it is totally starts changing, the slope is starts changing. Okay. So, in between these zone, if we want to withdraw the stress at any moment, so the material will regain its initial shape. Okay. Now, beyond that, if further we increase the stress, what will happen, that a point will come where without increasing the without increasing the stress, strain will start increasing. Okay. That means, the material will yield at this point, and beyond which, okay, even with less or no change of the stress, the material starts flowing. Okay. So, beyond this, if we want to withdraw the stress, we can't get back to the initial condition. So, beyond that zone, the plastic deformation will be there. Again, the stress will increase up to a maximum point that we normally define as sigma m, and after that the rupture will happen. That means, the material when fully exhaust, that cannot withstand the stress to a higher extent. So, it will break. Okay. So, this is a general nature of a material if we draw the stress strain diagram. So, here as I mentioned, that change in strain in response to increasing stress can be approximated by the linear function that will appear as a straight line through the origin, okay, on a stress strain diagram. So, modulus of elasticity is the slope of this straight portion, that is equal to d sigma by d epsilon, that is the differential stress divided by differential strain. Okay. Now, the condition is that we have understood that elastic and plastic deformation. So, this general phenomena we may not observe in case of the biological material. What happen in that case? For example, any food material, the sharp change from the elastic to plastic state is not visible in case of the biological material. So, for that what we do is that if we see that how the plot is look like, here the strain in percent we have plotted and stress is there. So, we can see that a gradual dome has been generated. Okay. There is no transition point, there is no fixed yield point. Okay. So, initially there was a linear region and then it starts deviating, okay, and then we are reaching a maximum stress and then rupture happen at point B. So, what we do is we fix a technical limit of elasticity, okay, that is used to specify the stress at which the permanent strain reaches a value of 0.2%. Okay. This reaches a value of 0.2% of the strain. Okay. So, that point we consider as yield point. Okay. So, this linear region shows the elastic behavior from which the slope will give the value of the modulus of elasticity, and here at this point we will consider the yield point based on the 0.2% strain if it generate in the body. So, the similar fashion we are calculating the modulus of elasticity, or this is also called the Young's modulus. We can also do the same thing for the bulk compression and shear stress, because we have know by now that there are forces where we can apply the axial loading or we can apply the bulk compression or shear force. So, we will eventually come on those studies. So, Young's modulus, as we have seen for any biological material, if we plot the stress and strain curve like this, so we will get a straight line portion. So, from the slope of the straight line we can get the idea of Young's modulus. So, Young's modulus gives an indication of how easily a material can be stretched or contracted, right, and is sometimes referred to as stiffness of the material. So, it is a property that is defined as stiffness of the material, right. So, here if we measure the angle, that straight line has been drawn with respect to the horizontal. So, that will be tan alpha. Now, stress is F by A, that is force per unit area, that is equal to E, which is Young's modulus, into delta L by L, that is the relative change in the length, or we can write F equal to E into A into delta L by L, and F is also written as D into delta L, where D means Young's modulus into area A divided by length L, initial length L. So, D is also called the Hooke's constant. Okay. So, next in a very concise manner we will just see that the different terms for interpretation of stress strain diagram. Okay. So, what will happen is that if we consider, if we first plot the diagram like the way we have done that, if you remember. So, first a straight line will be there, then it start decreasing. Okay. So, the elastic range, that means the range where we are getting d sigma by d epsilon, that is the differential change in the stress versus with the ratio of the strain, that is constant, that signify that strain is completely reversible. Okay. So, this is the status of the strain in case of the elastic range, and non-elastic range, that means d sigma by d epsilon will not be constant. Okay. So, in this zone strain is not completely reversible. Okay. Then d sigma by d epsilon, that is equal to 0, indicate the yield stress. So, the point at which it happened, the slope will be 0. So, that stress will be yield stress. Okay. So, from there the flow starts, okay, and the strain will be, strain continues without increasing stress. So, from this point onwards the strain continues without having change in the stress. Now, sigma max, when we reach the peak value where we can observe the highest stress. So, that is the maximum strength of the material, okay, and the corresponding strain we can measure, that will be the strain at maximum stress. This is not the maximum strain, this is strain at maximum stress. And technical limit of plasticity, because plasticity is actually the term is used when the material needs to flow. Some materials are there where as instantly the force applied on them and they start flowing, okay. Those are called the viscous material, but certain material are there where they need an initial stress to flow, okay. So, beyond that initial stress only they will flow, below that stress they doesn't flow. So, the technical limit of plasticity in case of the biological material we consider as epsilon, that is equal to 0.2%. If the strain reaches this value, so this deformation we can consider that yield point has been occurred and the flow starts. So, sigma will be the stresses for 0.2% strain which is considered as permanent strain, and strain goes to 0.2% of the permanent strain that we can measure. Now, rupture point where sigma shows sudden drop, okay. At this point when sigma shows sudden drop, that is the rupture point, and stress we can measure, that what is the stress we have applied here, and strain at the point of rupture we can measure what was the strain at this condition when the rupture has happened, okay. So, this is all about. Now, next is bulk modulus, okay. So, bulk modulus as I have mentioned already, that the body is compressed from all the direction, okay, x, y and z direction if you consider in a Cartesian system. So, the elastic range of compression and a non-elastic range of compression may be there. So, if the positive stress we apply, that is cause the pressure, so that will result in reduction in the volume of the sample. Or if the negative stress generated, that is expansion, so that increase the volume or the volume dilation may happen, okay. So, when the volume dilation can happen, that means if the product is under pressure, you are performing certain operation and suddenly the pressure has been released, okay. So, that is called a negative pressure and the volume will be increased. For example, if some of you have known the concept of extrusion, what happened in the extrusion, this is some kind of technique where we combiningly perform many unit operations like heating, cooking, and we also apply shear force on the body of the material that is being extruded. So, in the die, when the food is coming out of the die, okay, so it suddenly the pressure released on the body, because initially in the inside of the barrel, in the inside of the screw of the extruder, there was excessive pressure, okay, and shear force will be there. So, when it comes out from the die to the atmospheric pressure, so pressure release, that is why they expand and we are getting a very high porous structure. You might have seen in the kurkure and then many kind of this extruded snack item, okay. So, that happened because of this negative pressure, that is a case of a bulk expansion, okay. And So, next is now if we consider that element, okay, a block of the food sample, and then we are applying bulk compression from all the side on this. So, what will happen? Volume will decrease because this is a compressive force in nature. So, positive force. So, volume will be decreased. That is why we have written in this manner, that is minus delta V, that is the decrease in the volume of the initial volume V, that is equal to small k into dP. So, dP is the pressure change that is needed to cause dV amount of volume reduction in the sample. So, we can write small k, that is equal to minus 1 by V into dV by dP, right. Now, again we can write it as, if we write 1 by small k, if we write 1 by small k, that is equal to capital K, and that is equal to minus V into dP by dV. So, here what we can think of is that, so K is equal to minus 1 by V into dV by dP. K is termed as compressibility, okay, whereas when we write 1 by small k, that is equal to capital K, that is bulk modulus, okay. Bulk modulus, so the unit of the bulk modulus is in Pascal, and K is the compressibility in per Pascal, right. So, this we can think of as dP by dV by V. So, the pressure required to cause the relative change in the volume. So, it is the ratio of these two, okay. So, that is why we can term it as the bulk modulus, and it is decreasing because increase in the positive pressure will cause the reduction in the volume. So, minus sign has been given. So, the bulk modulus K characterizes how a material can withstand an elastic compression and is sometimes referred to as firmness, okay. So, first one, that is Young's modulus, that is the concept of stiffness we are getting there. Here what we are getting, that is concept of firmness, which is how a material can withstand an elastic compression, okay, elastic compression. Now, isotropic and anisotropic material, because sometime we handle the food material, those are not homogeneous in nature. So, because a food having the composition of carbohydrate, fat, protein and many other nutrients, okay, vitamins and all, and their distribution in the food matrix may not be same all the time, right. So, for those kind of isotropic material where the homogeneous property we can see, and there are certain okay. So, for the isotropic solid and normal fluid, the modulus K can be expressed in this manner, okay. There are 9 components, Kxx, Kxy, Kxz, Kyx, Kyy, Kyz, Kzx, Kzy and Zz, okay. So, bulk modulus in the normal direction, and also in the shear modulus, I mean in the direction of the other two faces. If you are considering the x directional direction, so x directional chain, that will also have effect on the other two direction, right. So, this is simply written as K equal to Kij, which is the bulk modulus, and small k, that is equal to 1 by capital K, which is the bulk compression. Now, what happened that if the material is isotropic, so when we are applying bulk compression or compressive force from all the side, so it will deform uniformly from all the side, okay. So, the structure, the size and shape that we will get, the size will be lower, but the shape will be same. However, in case of an anisotropic material, it will not be same, okay, because the compression, the bulk compression that we are giving, that will not felt by the material in all the side equally, because of their different property, they will behave in a different fashion. And another thing which is the shear modulus. So, what happened that as we have mentioned that if a dotted line dotted block is a stationary block kept on a surface, and then we start pulling the upper plate with a force F t, then what will happen, it is try to bend towards the horizontal side, it will be pulled down, and an angle will be made from the equilibrium position. So, that is gamma. So, this is a rotational change or torsional change, okay, and the angle of deformation is called here the shear deformation. So, if it has moved x direction in the direction of the applied force, okay, and the height between the two layer is y. So, x by y, that will be the expression of the deformation here, that is equal to tan gamma. So, shear stress is expressed as tau equal to F t by A. Okay. So, this is a tangential force is F t by area. So, this force is acting parallel to the surface, whereas the normal forces that acts on the perpendicular to the surface, and the elasticity is tau equal to g into tan gamma. For the small deformation, we can approximate tan gamma as equal to gamma. Therefore, we can write tau is equal to g into gamma. Okay. So, solids with ideal elastic behavior show a linear relationship between the shear stress and shear strain. So, solids with ideal elastic behavior will can give this kind of a equation. So, the material property G is called shear modulus and unit is Newton per meter square. So, we have by now familiar with the Young's modulus, bulk modulus and shear modulus. So, it gives an indication of how easily the material will be bent or twist in response to an applied stress, which is sometimes called rigidity. Okay. So, this is all about this different kind of modulus, and next is I will talk about stress tensor for a moment, because you might be knowing this concept in your fluid mechanics class or transport phenomena, but we are not going to cover all this heat transfer, mass transfer and momentum in our this fundamental course. However, just to give you an idea that how we can express them, because this term you may get sometime in the course. So, that is why we are expressing here is that stress is defined as force per unit area and usually expressed in Pascal, maybe tensile, compressive or shear, we know that. So, 9 separate quantities are required to completely describe the state of shear in a material. Basically, this is in case of a fluid in a flowing situation, we need this. So, if this element we consider here, so we are getting that there is sigma xx, sigma yy and sigma zz. So, these are the normal stresses. So, there are we can see that there is 2 suffix ij that is needed to express the stresses in this case, and the other stresses which is called the shear stress are x y, x y, y x, z x, x z and y z, z y. So, the point is that if we write the stresses in terms of sigma I j, I and j will be same for the normal stresses and I and j will differ for the shear stresses. Now, how we can explain this sigma xx and sigma xy like that, normal and shear stresses. Sigma xx will be the stress acting on a plane perpendicular to the x direction because of x directional force, whereas if we consider sigma yx, that is stress acting in y direction because of the x directional force. Okay. So, all this we can categorize all such forces, and whenever we want to discuss or we can analyze any such process, we can discuss that in which direction the flow is actually happen, because most of the cases we are handling unidirectional flow, and that time the other direction we may not need to take into account for the calculation. So, that we need to keep in mind, right. So, basically stress tensor is a state of stress at a point inside a fluid. The fluid in the deformed state can be summarized as stress tensor, written in the form of a matrix in this way: sigma 1 I j equal to sigma 1 1, sigma 1 2, sigma 1 3, sigma 2 1, sigma 2 2, sigma 2 3, and sigma 3 1, sigma 3 2, and sigma 3 3. So, generally this tensor is of symmetrical in nature under equilibrium condition. So, sigma I j will be equal to sigma j I. In that way, sigma 1 2 is equal to sigma 2 1, sigma 2 3 is equal to 3 2, and sigma 3 1 is equal to 1 3, and the diagonal elements are the normal stresses. So, we will stop here, we will continue in the next class. Thank you.